Hi, everybody. Welcome to our webinar today, Geoengineering, an overview of potential earth cooling technologies. I'm Joe Wachunas here with my team, and as always, Brian Stewart. We'll introduce you to our panelists in just a second. It's great to have you here. We always encourage folks, if you want to put into the chat where you are listening in from today, we always encourage that. So please go ahead. If I haven't enabled that, I'll do that right after the introduction. If this is your first Electrify Now webinar, welcome. We are an all-volunteer organization that believes that electrification is the easiest and quickest path to decarbonization. And we boil down our message into 4 key points. Clean up your electric supply through solar energy on your rooftop or community solar or your utilities clean solar program. Electrify your home. We have webinars and YouTube recordings on our YouTube page. Just Google Electrify Now YouTube, where you can find electrification tips on every part of your home. Electrify your ride, that same goes for that, be it electric bike or an electric car, and then Electrify Everyone. We've partnered with great nonprofits and raised a lot of money for great community-based organizations that are extending the benefits of electrification to all people, regardless of their income. And we want to say a huge thank you to all of you who donated as part of this webinar to help support our all-volunteer organization, Electrify Now. So thank you. And then a shout out, as always, to our Electrify Coalition. We're over 50 members and growing. If you're interested in joining the Electrify Coalition, there's no cost, so we welcome you to that. We want to welcome our newest member switching to electric as part of the coalition, so welcome to them. And thank you to all the organizations involved. Okay, and then a quick plug for our upcoming webinars for this month. Those of you who know or who have followed Electrify Now for a little while know that we do group a theme. We group webinars around a theme, usually in March. And so this theme, or this month, we are doing it on geoengineering. And so on Friday, we're going to be doing a webinar on solar reflectors cooling the Earth with surface-based mirror arrays. And then on March 28th, we're going to be doing a webinar, solar radiation management, research on atmospheric cooling technologies with one of the leading researchers from Harvard University. So really excited. All right. So Brian, we're talking about geoengineering this month. This is a little different take for us. Why are we talking about this topic?
Yeah, Joe. So as Joe mentioned, in March, we've in the last couple of years, we've done these themes around carbon sequestration, which again, it seems like our day job is about carbon avoidance and electrification, but carbon sequestration is obviously something that's been a really important topic for people. This year, we decided to focus on geoengineering. And I have to say, when Joe and I first talked about this, I think both of us were a little a little anxious about this topic. And some of you out there might have some of those anxieties. It sounds scary. Do we even need it? All sorts of questions arise. Is it a surrogate for not doing what we should be doing, et cetera? So I think we had some, anxieties that some of you might share about this, but I have to say, the more that I've kind of educated myself about this, the more I feel like it's a really important topic for us to be talking about. So I'm glad we're doing that today. And I don't want to belabor the introduction too long, but just a couple of things just to remind ourselves. I think most people would agree that the first priority when it comes to climate action is to stop the emissions that we're creating now. And of course, that's what Electrify Now is usually talking about. Things like solar and wind and EVs and induction stoves and heat pumps, et cetera. That's kind of mostly what we focus on. But I think there's an important realization that even if we do a really good job at those carbon avoidance mechanisms and solutions, there will be this giant amount of legacy emissions that remain in the atmosphere. Scientists say that somewhere between 5 and 15 gigatons of CO2 will need to be removed from the atmosphere every year, starting in 2050. And of course, that's a moving target because it depends on how quickly we decarbonize, et cetera. But the point is, there's huge amounts of emissions that we've already put up there that we have to deal with. And I think the second part of that story is that even in the best case scenarios, it will most likely take some time for us to draw those emissions down to levels that would be considered more normal or pre-industrial. And during that time, we are worried about the Earth's temperature continuing to rise. So that's why this conversation of geoengineering comes up, which is largely around heat, which you will see. But in order to kind of work our way into that, we have, I think, a fantastic panelist today we'll be introducing in a minute to help us kind of walk into this conversation with a little bit more knowledge and background and context that makes the conversation more understandable, beginning with the elements of the carbon cycle and how man has interfered with that or changed that cycle, and then how those changes affect what's referred to as the energy balance. So our panelists will help unpack what we really mean by that. But then geoengineering comes into the conversation because it's about changing this energy balance, and what problems are we trying to address with it? What does that term even mean? And then how does this kind of group of technologies that would be considered geoengineering technologies relate to other climate technologies that obviously we are already prioritized as being really important? And then what are the sort of solutions that have been commonly discussed in this area of geoengineering? And then importantly, it's good to know what the potential benefits are that, but equally important to know what the risks are and other issues that surround these technologies that we need to be well informed of and obviously understand, so that we don't just blindly try things that could end up being problematic. So I'm really excited to have our panelists with us today. Dr. John Perona, you may remember we've had him on the show before. He's a professor at Portland State University. He holds degrees, unlike most people, in multiple fields: engineering, biochemistry, and law. And I think it's because of this kind of interesting integration aspect to his career that he's not only authored all these peer-reviewed papers, but he teaches classes in these various topics and brings efforts to integrate those different points of view about engineering, biochemistry, and law and policy into the service of sustainability. He's the author of a great book called From Knowledge to Power, the Comprehensive Handbook of Climate Science and Advocacy. And Professor Catherine Hayhoe has called that a one-stop shop for anyone who wants to understand the fine details of climate science, past and future energy sources, and U.S. policies and political action to address the climate crisis. So I highly recommend that book if you aren't aware of it. It's a great primer on pretty much in every aspect of this conversation, including what we're going to be talking about today. So with that, I'm going to turn it over to Dr. Perona and let him share his screen and take it away. Oh, by the way,
I was going to say a shameless plug for John's book. I put a link in the chat, and yeah, please put your questions in the Q&A for John as we're.
Yeah, we'll try to answer some of those questions along the way, and if not, we'll elevate them at the end once we got through the presentation.
Well, thank you so much, Brian and Joe, for setting up this presentation for me. I'm really excited to be here and share what I know about solar geoengineering. In academic science, we often have meetings that we call journal clubs, and somebody who is not necessarily a total expert on the subject will read up on it and then share what he's learned to the group, and then there's a discussion. And so we might consider my talk today kind of be in this category. I have a very broad understanding of climate science and policy, and I'm not an expert on geoengineering per se. Fortunately, in this series, we have the third speaker, especially David Keith, is a world expert on the technologies that I will be introducing you to today. So my goal is sort of to lay the groundwork, provide the context for this field, and bring up some of the big issues around, what geoengineering is, how does it relate to other climate technologies, because we are not going to be able to avoid this topic. It's coming, whether we like it or not, right? And there are reasons to be concerned about its application. Okay, so I'm going to start with a little bit about Earth's energy balance, just because to understand geoengineering, we need to expand a little bit on our sort of underlying science toolkit. So usually what we do is in thinking about, let me see if I can get a laser pointer going here. Yeah, so the carbon cycle is where we usually start. So, humans have disrupted the natural carbon cycle. So as a consequence of the natural cycle at left on top here, we have the distribution of carbon in the biosphere. And so we have some carbon dioxide and methane in the atmosphere naturally, and we have a lot of carbon as fossil fuels in the deep underground where it's not part of the climate system. And then what humans, as we know, have done is extracted the fossil fuels, or some of them, and burned them and added to the carbon dioxide in the atmosphere. And that enters the natural carbon cycle on the surface. And about half of it goes into the land and the ocean over about a 10-year period. But the rest of it, which is a lot, persists for time periods of 100 years, 1,000 years, up to 100,000 years for the last few percent. Right. So we have, through the greenhouse effect, then temperatures rising for all this CO2 that's staying in the atmosphere. And using climate models, which are reflected on the bottom here, we can construct a carbon budget, which basically relates the amount of carbon that we have burned and what we can still burn, projecting how much carbon can we still put into the atmosphere while remaining below certain specified temperature limits like 1.5 degrees or 2 degrees. Using this carbon budget information, we then design renewable energy transition roadmaps, like we want to convert our electric power grid to all zero power sources, right? We want to go to electric cars, all the kinds of things that Brian and Joe do such a great job of promoting with Electrify Now. You can fit that all into a carbon budget. This saves X amount of carbon. So to think about geoengineering, and in particular, what we call solar geoengineering, we just want to add a little bit to this, right? We want to think a little bit explicitly about Earth's energy balance. So normally we have sunlight coming in. It's very energetic, and it's in the ultraviolet and the visible part of the light spectrum. But what's a little bit less obvious is that in order for there to be an energy balance, Earth also has to shine. And because Earth is a lot cooler than the sun, it shines with a different wavelength light, a much longer wavelength light, lower energy, and that's infrared light, like the light you get from a heat lamp. And over the last 10,000 years or so, there has been a rough balance in the natural way of things, where the input sunlight and the output IR have roughly balanced and a pretty constant temperature on the Earth up until the beginning of the Industrial Revolution. Right now that we're adding more greenhouse gas to the atmosphere, more of the IR is more of the greenhouse gas. There's more greenhouse gas, so more IR is getting absorbed. It's getting re-emitted back down. There's more energy in circulation here below where the greenhouse gases are in the atmosphere. And the only thing that can happen when that's going on is that the temperature goes up. And because we continue to add greenhouse gases today, the temperature is continuing to go up, and we keep on getting more and more out of energy balance, right? So there's one thing missing from this slide still, and that is the reflection of the sunlight. Okay, so without looking too much at the details of the numbers here, the sunlight's coming in like on the last slide, but some of it's getting reflected by the clouds in the atmosphere. Some of it's getting reflected by the surface. Here is the Earth light being emitted. Here is the back radiation from the greenhouse gases. Now, if we subtract the amount that's reflected from the amount that comes in, and we compare that to the amount that goes out, we see that there is a net amount of energy coming in as compared to what's going out. It's not zero, it's a net absorption of 0.6 watts per meter squared, where a watt is a power unit, energy per time per square meter of surface. And this is the data for over the last 10 years or so. So if we look at the total imbalance since the start of the Industrial Revolution, we have this very, very useful chart from the IPCC, which shows us that the Earth's energy imbalance is now estimated at not 0.6, but 2.7 watts per meter squared over the full period since about 1750. And that's about 1% of the energy flux. And we can see from this right away, very, very easily, the size of the bars on this chart reflects the respective contributions of each driver of climate change. And so you can see right away from this that carbon dioxide is the biggest issue in terms of the largest driver. Here is the methane, nitrous oxide, and halogens. There's a contribution from ozone. And so these will add up to this total with the further subtraction, though, of these cooling elements. So these cooling elements are also anthropogenic. Humans have warmed by all these reasons with the greenhouse gases. They've also cooled. If we hadn't also caused cooling, this number of 2.7, it might be 3.7, something like that. So I'm going to come back to this cooling effect of aerosols and land use change. So with this thinking in mind, we can sort of think about what are the leverage points. Let's say we want to be geoengineers. And what would be our leverage point? What could we do to rebalance the energetics of the Earth system? So one thing we could do is remove greenhouse gases from the atmosphere. And that's been a discussion, for example, direct air capture. And I'll come back to this. We could modify certain clouds, cirrus clouds, in fact, to allow more Earth light to escape, because cirrus clouds are warming clouds and they function like greenhouse gases. They're not the same as greenhouse gases, but their overall effect is to trap IR light that's shining from the Earth, just like greenhouse gases do. Or we could try to reflect more incoming sunlight, which is what we're going to spend a good deal of time on today. And that's usually what we think of as solar geoengineering. And I think this is it. There's no fourth option for what we might do to rebalance the energetics of the Earth system. So if we ask how much sunlight is being reflected, the term for that is albedo. It's the same as saying reflectivity. And the answer is about 30%. So that's how much sunlight reflects off either the atmosphere or the surface and does not affect the energy balance at all, right? It just bounces right back into space. It does not interact with greenhouse gases. It bounces back. So it's just as if it had never come in. Now, if we look a little bit more carefully at what is in that 30%, different surfaces, including the clouds in the atmosphere, and all the different variabilities on the land surface, they each reflect or absorb the sunlight to their own particular extent. And in particular, if something is very bright and white, like fresh ice and snow, it's very, very reflective. And if something is dark, like an ocean or a forest, then it's very, very absorptive. The albedo of forests is only 15%. Only 15% of the light, the sunlight that hits a forest reflects 85% absorbed, as compared to, say, an ice sheet, only 10% absorbed. So there's this huge difference. It comes out overall to about 30%. And in fact, we have been conducting an inadvertent geoengineering, if you will, experiment ever since humans started conducting organized agriculture, because our land use change is affecting the albedo. And that's what's shown on this slide. So if we look at the blue bar for land use, we see that there's actually been a cooling effect as a result of our land use, and that is from deforestation. So we cut down forests, they're very dark. We replace them with what? Grasslands, cities, things that are lighter, things that reflect more than a dark forest. That has a net cooling effect. So this does not mean that we should cut down our forests, because not shown here is all the carbon in the cycle that's trapped in the forest, that's stored, and is therefore not in the atmosphere. So that's a great benefit from forests that overrides this albedo contribution. Nonetheless, since we're talking about reflectivity today, we want to note that as a whole, replace a forest with, say, a grassland, and you have created a small cooling effect. Okay, so just to give you an idea of the power of this albedo, right? We have this positive feedback loop mechanism, which I'm sure many of you have heard about. Look at the albedo difference between this very bright white ice and this very dark ocean. And then think about what happens as we burn fossil fuels and increase the amount of heat that's trapped by the greenhouse effect. We burn a little fossil fuel, we melt a little ice, but then the white ice is turning into the blue ocean. The blue ocean is sitting right next to the white ice. Now it's all of a sudden absorbing a lot more of the energy than the white ice did, right? It's absorbing 90% of the energy or something close to that. So that means we heat more, we get more heat, and now more ice melts, right? When more ice melts, it turns into blue ocean and we get, right? So it's a positive cycle. And so this is really the explanation for why the Arctic is warming so much faster than, say, the temperate regions in North America. Okay, so if we go back to this chart, we can see that the other big blue bar here that is promoting cooling because of human influence is the aerosols. And we are generating aerosols largely as a byproduct of the fossil fuel economy, right? All the smog, all the particles, everything that we're doing by burning fossil fuels. As we transition away from fossil fuels, that blue bar is going to get smaller and smaller over time. It's going to unmask more of the warming. This will happen slowly as we conduct the energy transition. But adding the aerosol, adding more aerosol is the basis for solar geoengineering, which is our topic today. So, we have a nice big blue bar. Let's make it bigger. Right. So that's it. That's the idea of solar engineering. Reflect more by adding more aerosol into the stratosphere. Okay. So that's a little bit of primer to get going with. And so what I'd like to do now is to think about the relationship of solar geoengineering in particular to other kinds of climate technology. And we'd like to see if we can kind of understand, like, what is this geoengineering? I've kind of suggested we're already doing it inadvertently just by changing land use over the last 5,000 or 10,000 years. How do we categorize geoengineering? Is it an adaptation? Is it a mitigation? Does it get at the root of the climate problem or not? Right. So one suite of climate technologies falls under the heading of adaptation. And this can be very simple. It can be things like creating local support networks, community centers for cooling, paying attention to impacts to low-income communities where there's less resource to adapt to the climate. And then there's other larger scale kinds of constructions that we also consider adaptations. The key common element, though, being that all of these climate technologies are addressing the consequences of climate change and not the cause. So climate change is already happening, and we just need to be able to deal with it. And that is certainly part of what we are having to think about and devote some effort and resources to. Right? I mean, some of these adaptation projects get pretty big. So if you're looking about the coast of Louisiana, the sea level is rising there faster than anywhere else on Earth, in part because of oil drilling in the Gulf of Mexico, which is promoting land subsidence at a rapid rate. And so there is now a $50 billion envisioned project in Louisiana, all adaptation to try to deal with the rising seas. I mean, think about the size of the Oregon, but so Louisiana is like the size of a little bit bigger than Oregon, right? If Oregon had to spend $50 billion considering our budget, think about what kind of effect that would have on everything else we're trying to do. So, and then this adaptation has its dark side. Like we want to protect the cities, and then the water has to go somewhere, right? So another kind of adaptation that brings us closer to what we're talking about today is this idea of managing heat by reflecting some sunlight locally. And so we're talking about reflecting sunlight globally, but we're already doing things like painting urban roofs white, brightening the pavement. And that has great effects positive adaptive effects. So we can reduce the amount of heat in an urban island. We have health benefits, of course, from that, from less heat burden, save a lot of energy on air conditioning, for example. Or there's also a set of technologies that involve increasing the albedo or the reflectivity on farms. So if we use no-till farming and we leave some residues in the ground, they tend to have higher albedo than the bare ground. And there are some other methods involving changing the timing of the plant life cycles, even breeding plants to have more reflective leaves, whether traditionally or even by genetic engineering, to reflect more, to preserve the crop and all its benefits, whatever we're doing with it, but also have it be reflecting more light, right? So all of these are adaptations. So then there's another set of technologies that we call mitigation, which is directly addressing the causes of climate change. And here we're talking about the kinds of things that many of us are familiar with and are working on, things like converting the electricity grid, switching to low carbon fuels. This is a Building Energy Efficiency Week in the Oregon legislature. The relevant Senate or House committees are considering a whole suite of bills to improve the energy efficiency and reduce the emissions from the building sector. So this is all about, we're doing things through just the way we live. We are emitting a lot of fossil fuel. We're going to mitigate that by either fully eliminating or at least reducing the fossil fuels that we emit. And so that's a mitigation. Here's another kind of mitigation. It's carbon capture and storage. In, for example, hard to electrify manufacturing industries, like fertilizer production, like petrochemicals, like cement manufacturing, like hydrogen production, industries that are hard to electrify. We can capture a good part of the CO2 and safely sequester it in geologic reservoirs underground. And to the extent that we are trapping and burying some of that carbon and putting it out of the climate system by putting it deep underground, that's also a mitigation. This is made relatively easy by the fact that the fraction of CO2 in a smokestack emission depends on the industry, but it can be somewhere around 10%. Compare that to the dilute CO2 in the atmosphere, right? So I'll come back to this idea. Okay, so we have adaptation and we have mitigation. And so then we have another set of climate technologies that we're at least thinking about, right? And so what about the idea of afforestation, planting or reforestation, if it's land that used to be forested, afforestation if it's land that has never been forested, right? What should we call this? Clearly, if we're in this urban environment, for example, and we want to plant some new trees, then we can alleviate the urban heat island effect by doing that. We can store some carbon. So we're adapting and we're even mitigating a little bit. But what I'm talking about here is looking at the surface of the earth and thinking, we could fit 3 trillion more trees on there. And if we did that, we'd move a whole bunch of carbon from the atmosphere onto the land, right? You could call that mitigation, but I'd like to distinguish between the kind of mitigation that we do to change the way we live versus looking at this big picture of the planet and saying, we want to store more carbon away from the atmosphere. And one place you could put it is on the land, right? So maybe we could consider the idea of planting 3 trillion trees as geoengineering, because we're deliberately moving carbon from one reservoir, i.e. the atmosphere, to another one, right, the land, okay? So then what about this, right? What about direct air capture and possibly other similar technologies like enhanced weathering? But direct air capture seems to have the most promise at the moment. And indirect air capture, we have to capture CO2 from the ambient air with this set of fans here on the left, which take a lot of energy to run, by the way. And then we have to react to CO2 with an amine, a chemical that will react it on a solid sorbent is the best technology, and then release it, compress this captured CO2, and then transport it through pipelines and safely sequester it underground. You could also imagine using some of it in a sort of marketable way, as for example, building materials. But most of it, if this technology develops, is going to have to get injected underground. So now we're talking about taking carbon from the atmosphere and not moving it onto the land, but moving it into a reservoir deep underground that is not part of the climate system over geologic time, right? Now, eventually, there's a long-term geologic cycle, but we're not concerned about that. We're just thinking it's out of the atmosphere, and it's permanently out of the atmosphere as far as we're concerned. Right. This technology has near unlimited potential because there's truly enormous amounts of reservoirs to bury the carbon in. And the technology is also overlapping with the industry carbon capture and storage, in the sense that for a lot of this, it's the same amine reaction to trap the carbon. And the CO2 pipelines would be commonly used, and all the technology to bury the CO2 in the underground aquifers would also be the same, right? So it's kind of like industry CCS helps pave the way for direct air capture. So I would say most people probably think that direct air capture is geoengineering, right? As opposed to, say, mitigation per se, because we're just looking at this big picture and, plant 3 trillion trees, bury all the carbon from the atmosphere, one way or the other. And then we can finally compare this to modifying the reflectivity of the atmosphere, right? And so we can ask, so what is this? This is clearly geoengineering. If we want to call geoengineering anything, we would have to call it this. It's solar geoengineering, in the sense that we're actually changing the amount of sunlight that makes it to the surface by reflecting more of it away in the atmosphere, right? And this, if it works as projected, would cool us off. But what this really is a form of adaptation, right? It's like taking the white roofs in the city, cool us off a little bit locally, and cooling off the entire planet by adding a layer of aerosols in the atmosphere that would spread over the entire Earth and cool the entire Earth, right? So we cool off, but it seems pretty clear that we are not addressing the root cause of climate change. Underneath this blanket of aerosols, we might be continuing to burn fossil fuels in the same way that we're doing now. But we can get as cool as we want, just put up more aerosol in the atmosphere. So I think that this is properly thought about, yes, as geoengineering, but also as adaptation at a global scale, and it's not mitigation. Okay? And it doesn't get at the root cause of the climate problem, which is the buildup of carbon dioxide in the atmosphere. Okay, so let me move on then and talk about some of these actual technologies. And again, the world expert on these technologies is coming to give us a seminar in a few weeks. And so I am going to give you an overview of what I've learned about these technologies and their potential benefits and hazards, and a little bit about how they would work. And so on this slide are the 3 main technologies that are thought of as the atmosphere-based interventions, the ways in which we might modify the energy balance by modifying the atmosphere. And so one of these is stratospheric aerosol injection. This is the one we'll spend most time on. This is one that's the most thought about, the most modeled by climate scientists, like Professor Keith, who's going to be here in a few weeks. And this involves adding aerosols to the atmosphere, into the stratosphere, I should say, so high up above the troposphere, and reflecting more sunlight. The second method is called marine cloud brightening. And this is spraying sea salt on the tops of low-lying marine clouds to get them to reflect more solar radiation. Okay, so you can see from this drawing that we've got the reflection up in the stratosphere here. We've got the reflection way low, 0 to 3 kilometers high, low marine layer clouds. Let's have that scatter more, reflect more radiation. And then the third method is called cirrus cloud thinning. And this is where the warming cirrus clouds that work analogously to the way that greenhouse gases work, in the sense that they absorb Earth light in the infrared and re-emit some of it down to warm us. Well, if they're going to warm us the way they are now, why don't we just thin them out a little bit? We'll thin out the cirrus clouds, and then there won't be as many of them. And then they won't be able to trap as much Earth light, so then more will get out and will be cooler, right? That's the idea. So the cirrus cloud thinning operates on the IR side of the balance, the outward energy, and the other two interventions operate on the inward part to actually reflect more sunlight, right? So we could ask, why are we even considering doing this? And we do not need to belabor this point, because we know that we are in a climate crisis that is getting worse. And, there's really a concern that we may not be able to keep the temperature within levels that are tolerable. And so just on a strictly humanitarian basis, and I do think that many of the scientists who are thinking about solar engineering are motivated by humanitarian reasons, would like to have ready, if we need it, a technology that can rapidly cool the planet and mitigate at least some of the concerns that you see here on the IPCC chart, right? So we're at 1.2 degrees now, or somewhere over here. You can see we're sort of, no matter which of these reasons for concern RFCs we're talking about, and here are some of the areas in which what these RFCs refer to. We're kind of in the moderate to getting worrisome parts of the spectrum here. And as we go, say, from 1.2 to 1.5 to 2.0, then the impact is going to get worse in all of these categories. And both the UN and the International Energy Agency are projecting that with present policies, we're going to end up somewhere between 2.5 and 3 degrees. It looks like we've averted the very worst case outcomes, which used to be considered to be 5, 6, 8 degrees C, flipping over to hothouse Earth conditions. But we don't have to project that kind of catastrophe to be very worried about, for example, what 2.5 degrees would be like. Much worse than we have now, right? So that's why. So we have these three main approaches to atmospheric modification, as I just mentioned on the left. And I just want to quickly mention a fourth approach, which is enabled now by what we would call space payload technology, i.e. SpaceX, right? In case you want to further develop your virtual relationship with Elon Musk, consider that he is thinking about sending 1,000 spaceships back and forth to Mars. And some of what they could be doing, I don't think he's actually said this, but it could be to assist in the building of a solar shield, which would be mirrors in space that would reflect away the sunlight, right? This is pretty, I'm reading a few papers in this. I think it's pretty nuts myself, but nonetheless, the conversation is gaining more ground because people are thinking about this kind of space technology that seems to be really developing. There are what are called Lagrange points in the Earth-Sun gravitational system, L1 through L5 up here. The idea is to put the mirrors at L1, and a Lagrange point is like a point of balance where the gravitational forces of the Earth and the Sun and the centripetal forces of the Earth's orbit balance each other out, such that when you send a spaceship there or you build a structure there, it tends to stay put, more or less, because there's some kind of balance of forces. And so we build it at L1, which would be right there. I think it's like 10% of the way to the sun or something like that, or maybe 1% of the way, I don't remember. And you'd build this enormous mirror, right? Reflect enough sunlight to reduce the surface temperature by 1 to 2 degrees, which would be about a 1 to 2% reduction in the incoming sunlight. That's probably a reasonable number. But the size of this thing is unbelievably large. You can see here's a sunshade island, 450 kilometers here. 22 of these would be needed to cool Earth to 1.5 degrees, given some assumption about how hot it gets. So you'd have to launch pieces into orbit. You'd have to use solar radiation pressure, the solar wind, to get them to come together at the Lagrange point. There are other papers that talk about establishing a lunar base and launching from there, mining the moon, mining asteroids, believe it or not, for the materials to build this enormous structure. Okay. I mean, I found $2 to $4 trillion cost in the literature. I think that's a massive underestimate probably of what this would cost. But I don't think we need to be concerned to think too hard about this in the time frame of, our present climate crisis, because it's well beyond, despite new space launching technology, it's pretty well beyond our capacity at the moment. Okay, so when we talk about stratospheric aerosol injection, which is the atmospheric modification, the method that is getting the most attention now, introducing aerosols into the stratosphere, there's a lot of impetus for this that's coming from the explosion of Mount Pinatubo as a natural modification, right? So what happened in 1991 is the volcano erupted and injected a huge amount of sulfur aerosol into the stratosphere, where it cooled the Earth by almost 0.5 degrees C. You can see this on the chart. And then it took 2 or 3 years for the temperature to recover fully, right? And so this actually is somewhere along on the scale of what is envisioned that we might actually do by solar engineering. More than 0.5 degree, maybe 1 or 2 degrees instead of 0.5 degree, but still pretty close to this scale. And so using this with all the, we know exactly what happened. We know where the particles went. We know what they were. We know how they got distributed. We know how long it took to cool. We know how much cooling there was. We know how much the Earth's albedo was increased, 0.5%. Like think instead of 30%, it's now 30.5%. So now we can think, okay, we can do models and we can compare to this actual natural experiment and say, okay, let's say we want 1.5 degrees of cooling. We need 3 Pinatubos. But we need to keep on doing it, right? Because the cooling goes away, the aerosols settle out, right? So this is driving most of the computational research. It goes into thinking about, well, what could we do with sulfur aerosols? Because there's this natural model to compare the computational results to, right? What are the plausible benefits of stratospheric aerosol injection? So there's actually the potential to cool the Earth by several degrees within a few years of deployment. And it's the only approach that we know of that could possibly accomplish this. So if you're thinking about, strict humanitarian benefits, the temperatures, it's intolerable in certain parts of the world. We can alleviate that burden. If we had a way to alleviate that burden on Earth, we would probably do it, right? We would certainly, just on humanitarian grounds, we would do that, right? Well, here's how we can do it for the whole planet. The models are not very good yet, but they're certainly good enough to predict, confidently project that there would be a cooling effect. They are also predicting regional effects that are much less predictable and they're pretty model dependent. It's affordable. I've even seen papers that with cost estimates of substantially less than tens of billions of dollars per year. So this might actually even be an overestimate. And it seems to be feasible. People who are thinking about, well, how would we actually do it? There's no insuperable technical hurdles. What we're talking about is flying airplanes into the stratosphere, right? And delivering the aerosols, delivering sulfur dioxide, which we manufacture now in industry, which is made from sulfur, elemental sulfur in the Earth's crust, which is not infinitely abundant, but there seems to be a fair amount of it. We wouldn't have a resource problem, at least not right away. And then the sulfur dioxide reacts to form sulfate aerosols. By spreading them in the stratosphere, it's very low turbulence, so you get an even spread. The release would be at about 20 kilometers altitude, so the low stratosphere. And there's even papers that project, well, how many flights would we have to do? How much would we have to deliver? The idea would be to be something on the order of 4,000 flights in the first year, and then there'd be more in subsequent years. A megaton, 1 million tons of sulfur in the first year, and then more. Thinking about alternatives, and that's important, especially with respect to other aerosols, because as we'll see in a second, sulfur aerosols have specific hazard potential to them. And then, how long will we have to keep this going? Depending on the pace of the net zero energy transition, we might need to keep it going for a pretty long time, right? So what are the variables here? How high do you release this aerosol? Where do you release it? At what longitude? At what latitude? How much do we release? What time of the year do we release it? What exactly is the chemical nature of the thing that you're releasing? It seems plausible from the modeling that one could target regional effects, like let's cool the Arctic. It is not plausible to imagine that China will launch an aerosol attack on the U.S. and cool out Miami Beach, but by targeting aerosols right over there. Right? There's no concern about country to country targeting, but possibly directing the aerosols to do specific regional cooling might be possible. But if you look at this graph here, again from the IPCC, and you look at the size of the error bar where my cursor is on the aerosols, it's huge, right? And this says that the basic radiation physics, the basic understanding of how radiation interacts with matter in the atmosphere is weak, right? And this is one of the major reasons why climate models are not yet very predictive, right? They don't help guide our policy as well as they could if we understood this physics better, right? And that if we did do research on solar engineering, computational only, say, we would perhaps yield a great benefit in terms of understanding the climate system better, and then being able to use that in all our climate work.
Hey, John, sorry, just to interrupt just on this point, because I think it's an important one. Looking at, because I think what you're pointing out is the error bars on these other dimensions that are listed here on that chart are much smaller. So we
Yes.
So we understand the effects of carbon dioxide a lot better than we understand the effects of aerosols, basically what this is saying, for example.
That's exactly what it's saying. Yes.
And then that looks also like you could deduce from this that the error bar on the total anthropogenic is largely a result of the error bars on the aerosol.
Yes. Yes, the error, if we understood the aerosols better, then the error bar on the total would be a lot smaller than it is.
Yeah, that's interesting.
That's certainly fair. I mean, clouds are one thing we don't understand well, and the other thing we don't understand well is the complexity of the land surface and how the land absorbs carbon in the carbon cycle. Those two are the big areas of climate modeling where we need a lot more research. Okay, so that's the stratospheric aerosol injection. Just a quick mention of the other methods. Marine cloud brightening is a completely different technology. So here's Gibraltar, Spain and Morocco. Excuse me, here are clouds over Europe. These tracks here are ships in the ocean letting out aerosols, exhaust from their engines. The idea here is that we would have nozzles from deployed ships in areas where there are low marine clouds that would spray sea spray up high enough to get on the top parts of the low marine clouds and increase the reflectivity of those clouds by having a very large number of small little droplets. And large numbers of small droplets increase reflectivity, right? So it's not clear to me from what I've been able to read that this targeted deployment would be able to ever have a global reach. I know that there are some people who think that. It's a good question for David Keith. But maybe targeted deployment for local cooling, which might have, people would be less worried about. It's not really a global effect. If you have a coral reef area and you really need local cooling and you're trying to save the reef, for example, and this is a way to do it, maybe that would be an acceptable thing to do. But a lot more work. None of this has been done in practice. Of course, a lot more work would need to be done to figure out how to do it. And then the last method is cirrus cloud thinning. A cirrus cloud, unlike a cumulus cloud, is considered to be a warming cloud because it absorbs a fair amount of Earth light and then re-radiates it back in the same way that not the same mechanism, but analogously to the way the greenhouse gases do this. And if you look at the right, these little white stripes are contrails for jet planes in the Southeast US. When 9/11 attack happened, air traffic was grounded for 3 days. and those contrails went away. And there was this huge climate effect from that in those 3 days. There were higher highs, the higher temperatures during the day with no contrails there because the contrails reflect some sunlight. There are also colder nights because the contrails weren't there and the contrails absorbed some earth light. And the effects were like 2 degrees one way and the other. So it was a pretty big effect. And this experiment didn't establish, because it was just one piece of time, but it was kind of like this inadvertent experiment that showed how much effect you could have from something that behaves like a cirrus cloud, right? And so the idea then is if we could thin out the cirrus clouds, it'd be kind of like making the contrails go away, as long as the warming effect dominates, which we think it would, right? So cirrus clouds have small particles that self-nucleate, they're just ice, or they can grow ice around some dust particle or some other little particle. And the small particles absorb more earth light. So if we seed these clouds and we favor the large ice crystals, we would promote net cooling, right? And the large particles might fall out more, the clouds might get what's called thinning, right? We don't understand this very well at all. There's nothing I can find in the literature about how one would actually do it. Presumably, perhaps, and these are high clouds, so something perhaps similar to the stratus aerosol injection, but you don't have to use sulfate aerosols. Okay, so I want to finish up. I know we're probably running a little bit late already. I'm just going to finish up by talking a little bit about the hazards, benefits, and what people think about this. So pretty clearly, if you look on here, surface temperature down, cryosphere melting rate down, extreme events down, rate of sea level rise down just by lowering temperatures. We can project, the models project that these kinds of beneficial effects at the global level would occur, while not knowing what would happen at the regional level. But there are also some new hazards here. We are actually changing, by doing this, we're changing the amount of direct sunlight that we would receive compared to the amount of diffuse sunlight. And that is projected to have consequences on the efficiency of photosynthesis, possibly on crop yields, possibly on the ability of solar thermal plants to generate electricity because they need direct sunlight. The models are showing fairly strongly altered precipitation patterns regionally. The amount of rainfall seems to decrease pretty fast in these models, faster than you would think. Lots of work would need to be done on this, but it's certainly a new kind of hazard that we would not understand very well. If we use sulfate aerosols, then it's pretty clear that they would deplete stratospheric ozone. If we did this for many years and injected a lot in the aerosol, we're talking about, I've seen numbers 20–30% depletion of stratospheric ozone. So kind of like backtracking on our progress of healing the ozone hole if we used sulfate aerosols. And similarly, these aerosols also absorb some radiation. They don't only reflect it. And there would be some heating in the stratosphere, and that would propagate to have other climate effects. So this is a reason why some folks who are thinking about this would like to use some kind of different aerosol, and possibly calcite or calcium carbonate. Right. Other effects, ecosystem health, who knows, agriculture, largely unknown, human health, kind of downstream effects. It's hard to know what would happen. Right. So for the reasons of these increased hazards and other reasons, there is a fairly strong voice to enact a non-use agreement, calls for an immediate negotiation banning the deployment of this technology in all outdoor experiments, so that we never do it, right? And the idea is that this would prevent, so we could call for a ban on state funding of the technology, still fund basic climate research, right? But ban all outdoor experiments. Any deployment, if a third party comes along and says, I have this great idea, no government would support it. No patent rights for the technology. The UN, for example, would not allow this kind of method for a country to say, this is how I'm going to, deal with the climate problem in my country. We're going to spray ourselves. No, we would disallow that. That's what this calls for. And you can take a look at the citation. And so the question is why? Why is there this strong opposition? huge ecological threats, massive humanitarian risk for the most vulnerable, fundamental geopolitical challenges. Moral hazard, why work so hard for mitigation, reduces the urgency, but also who gets to decide, right? Rich northern countries who are doing all the research and have all these smart scientists and they're controlling the UN and other agencies. They're the ones who get to decide. There's a strong equity dimension here. There's no way to do small scale outdoor experiments. I mean, you could do them, but they would not help. It's like you're either going to do an experiment that has a measurable effect so you can see what happens, or you're not going to do them at all. So you might as well not do them at all. The problem is you create a constituency of people, even doing some, even computational research could do this, where you start to want to see like what would happen if we really did it, like it's a slippery slope. And a lot of people are concerned that that's real. And then finally, and this is just summarizing some of the points, stable international governance is implausible. Look at the world today. Do you really think we're going to be able to like manage this kind of thing? Maybe we believe that many of the scientists are well-intentioned, humanitarian objectives, but they're not going to control what happens here, right? The Donald Trumps and the Putins and maybe the Elon Musks of the world are going to be making the decisions here. And more, this is so cheap and so easy to do, it's perceived, not that we're, it still takes some effort to get it going, but that unilateral action by specific countries seems possible. So we need a strong no from the international community and sanctions and whatever. This is not something you can do, right? There's a lot of questions about the validity of the models. Not all of this is very well informed necessarily, but it is true that greenhouse gases heat the planet by one mechanism, right? So we've done this we've done this experiment. We've lived in such a way as to put all these greenhouse gases in the atmosphere. We've massively unbalanced the energy, and now we're going to try to fix that by rebalancing the energy. But we're going to, instead of doing it over here on the output side, we're going to rebalance it on the input side. So now we have another massive intervention over here, and we're going to kind of hope that it works out. Like we've messed it up here, and we're going to try to fix it here. So now we've got these two big things, and we're going to kind of hope that it works out, right? And then finally, there's just a moral revulsion, right? This is in the category of nuclear bombs, modifying the human germline, constructing a new COVID virus that has some new cool parts. I mean, maybe we'll learn something about things, right? Maybe we shouldn't do those kinds of experiments, period, right? It's in that category of stuff. All right. Nonetheless, as far as research goes, and this is not about deployment, but as far as research goes, the UN is recommending a process. The National Academy of Sciences, the NAS, did a comprehensive study, is recommending a research process. The Biden White House has started a study plan in their OSTP. The Congress is now talking about it. As a Congress watcher of climate energy things, it looks like they're probably going to do something. They want to show that they're doing something, and throwing $500 million at NASA for this kind of thing is not that big a deal. So you've got some bipartisan statements here. Even Sheldon Whitehouse, who has made statements along the lines of the criticisms I just offered from the community that wants to ban this stuff, is now saying, well, knowledge never hurts. But again, this is basic research. This would not be deployment. All right, so I want to finish off by contrasting solar geoengineering with direct air capture, because I think the contrast will allow us to be clear about the distinctions of these technologies, and so we can think more clearly about which one do we want, if either one, right? So we know that they work by different mechanisms. The duration of the cooling, we saw the Pinatubo experiment, 1 to 3 years. For marine cloud brightening, it only lasts about 10 days before it goes away, right? On the other hand, you remove atmospheric CO2 by direct air capture, it's permanently sequestered underground. And with direct air capture, we're talking about from the atmosphere, trap the CO2, compress it, pipe it, pump it underground, that whole process. Atmospheric CO2 level, high levels persist. DAC decreased to desired level, right? So maybe net zero is not enough. Because even if we do the greatest transition we can imagine, we're going to come out at 460 ppm, say, right? We're going to have 1.8 degrees of warming, right? We're going to have massive impacts, much worse than today with that, right? So maybe what we need to do is to think about going below 460, 400, 350, right? There's a whole organization called 350.org. Maybe we want to go all the way to 280, pre-industrial. And there's virtually unlimited potential for DAC because the underground reservoirs are huge. There's plenty of places to put this stuff. We could do this fast, but we'd have to continue indefinitely. This would take a longer time before the cooling would be measurable. But then once you're done, you throw the technology away, right? You can just stop, right? So here green indicates favorability. Ocean acidification improves with DAC because the CO2 would degas once you're taking it out of the atmosphere. Doesn't improve with solar geoengineering. It might even get worse. Termination shock. I have not mentioned this. What if we're doing this technology and then there's a war, there's another pandemic, who knows what happens, it stops. I don't want to be around in those few years after it stops, right? Because there's going to be this massive heat shock, right? Like, and that would cause effects like, like we've never seen, right? No termination shock for DAC. Development time and cost, much more favorable for solar geoengineering, right? But this DAC, this cost is still prohibitive, but there's good reason to think it's coming down. And finally, we talked about some of the hazards of solar geoengineering. DAC has all the hazards are known. We do have to scale up the process. And the process could work within the UN framework. Countries would just say, well, we're going to do some DAC. There's much lower potential for societal conflict, I think. And finally, whereas solar engineering, we're talking about, okay, let's allocate some funds for directed research. In the US, we now have this massive tax credit for direct air capture from the atmosphere to bury, $180 a ton. Still not quite enough, but very, very high, amazing credit. We're building CO2 pipeline infrastructure with the infrastructure law and the Inflation Reduction Act. And EPA already regulates the sequestration, the pumping in of CO2 in underground class 6 wells. So I will stop there. I guess you guys can all tell which technology I favor. And thank you all for your attention. And these are some good references if you'd like, especially the first one, very readable, 20 or 30 pages. You'll be completely up on the technology, on the status of things for that, and the longer one from the National Academy. So thanks, and I'm happy to answer questions.
Thanks, John. Yeah.
Great, thanks, John. That was fantastic.
Some folks were asking if we will definitely send the slides and the presentation to folks tomorrow. So that's what we always do. Yeah, Brian, you have a
yeah. So I think I want to dig in a little bit to this learning without doing topic a little bit, because it sounds like you were saying and other people are saying that it's important to understand this better and to research it more. I've heard that from other people as well, that there's a lot of just basic understanding we need to gain. But do you imagine, you talked about the slippery slope thing, so which was partly answering my question maybe, but can you talk a little bit about this? Can you imagine a scenario where we're learning this without actually having to try it in order to learn what we need to know? I mean,
yeah, I mean, I can imagine that, because I mean, the computational climate modeling community is large and robust, and this would be the funding that we anticipate now from Congress, directed funding, would target an area that is understudied and we really need to learn about. And so the benefits are very strong, very, very good benefits from that, generally, not having necessarily to do with this technology. It is true that some of the computational experiments for sure are gonna some of the grants are gonna fund questions like, if we put this much calcite aerosol instead of sulfate aerosol in these places around the atmosphere, with this kind of deployment over time, what happens to sea level rise? And so there'll be like a gazillion experiments like that. But all those experiments will also inform the basic system, because it's a common thing to do in science is you perturb the system and see what happens, and then make inferences about how the system works based on that. So, So, I could see it. It kind of depends on the institutional response and the how loud the voices are and how effective they are to, oppose the deployment, right? I mean, the research, the computational stuff, I mean, whether climate modeling scientists who specialize in the atmosphere, whether they have directed funding or not, they're going to do the experiments. They've been done. There's a literature on it, right? And it's going to continue one way or the other. I think it's more about how we organize around it. Like, do we want to, really highlight the issues?
Hey, John, you addressed this right there at the end, but I wonder if you maybe just emphasize it a little more. Some folks were just wanting to understand if it would affect ocean acidification at all, if geoengineering would help ameliorate that problem. And from your chart there at the end, it says no, but just maybe say another word or two on that since we touched on it briefly.
Yeah, well, I mean, ocean acidification occurs because the oceans are absorbing, a sizable chunk, 20 or 25% of what we emit every year is going into the oceans. And when CO2 dissolves in the ocean, it forms carbonic acid, and that dissociates to protons. And so you have an increase in acidity. If all you do is block the solar radiation from getting in, you're not doing anything about the CO2 level underneath. And so you're not changing the dynamics of the CO2 going in and out. If you actually remove the CO2 from the atmosphere, then there's going to be a response in the natural system. And the natural process of evaporation and dissolution of CO2 from the ocean surface is going to be, as you take CO2 out of here, it's going to go farther this way because you've removed some. And the more you remove, the more comes out, right? Now, it's more complicated than that, but that's, a key mechanism that's happening. And that's not going to happen if you don't, you can just, if all you do is block the sunlight, you're not affecting the CO2 level. Now there are arguments that by blocking the sunlight and cooling, you will stop the runaway carbon cycle feedbacks that are positive. So for example, the permafrost might not melt so fast. We cool enough, we stop the melting of the permafrost, therefore we stop the emission of CO2 and methane from the melting permafrost if it's cool, right? And if we get worried about, things look like right now, it looks pretty stable, not large emissions, but if we get to the point, it's 2 degrees of warming instead of 1.2, and it looks like the permafrost is really unstable, and it's going to give a huge climate shock, that would be a pretty good argument for deploying this stuff.
Right. I was going to ask you about that. So it's sort of like, and maybe this is just speculation, but I mean, I imagine a situation where things are starting to look really dire, and then this becomes more attractive, or not attractive maybe, but more kind of justifiable maybe is the right word, I suppose.
Just on humanitarian grounds. I mean,
Yeah.
Clearly, the best thing we can do is make it so that we don't ever have to do it.
Right.
And it could be if we have our act together on the renewable energy transition, it could just be redundant with direct air capture. Like if we have direct air capture working and we're bringing down CO2 levels and we've stopped them from getting too high because we've done a good job with the energy transition, then we're not going to need this stuff, right? So that's what we should be working for. I am a big.
That's interesting. So, I mean, do you envision it? Is there a scenario where you're doing some of both? I mean, I don't know. I'm just asking. Like, is it conceivable that you're doing some modest amount of energy balance work, while you're doing this direct air capture, and you kind of like weave all these solutions together in a way? I mean, is that or do you think it feels really either or?
No, it's not either or, for sure. I mean, it's definitely possible. I mean, in fact, David Keith has written about how the best policy might be to do some like modest cooling, like limit the hazards by not, trying to cool, by a huge amount, but kind of take the top off the worst of the effects. while we're removing carbon from the atmosphere. I don't know if he said the latter thing, but I would say, there's room for nuance in this. And you can potentially limit the hazard by not injecting that as much aerosol.
Right.
Good.
Well, we are about 10 minutes over. I actually do have to run into another call. So I think, any last burning questions, Brian, you wanted to ask?
Well, I have a couple, but one, how about just one? The word sulfur to me conjures up this toxic, nasty thing, sulfuric acid, etc., acid rain. I don't know. So can you just speak a little bit to that? It just feels a little bit like, it just sounds like pollution when you say injecting sulfur into the atmosphere. Am I misreading that or?
Yeah, I mean, a little bit. Mount Pinatubo polluted the atmosphere by injecting massive amounts of sulfur into the stratosphere.
Mm-hmm.
And sulfur is a naturally occurring element. It's essential for life. We all have sulfur in our bodies. It's true that, one form of it is acidic, and, coal-fired power plants belching sulfur dioxide in the Midwest in the 1980s, acidified the Great Lakes until we put a stop to that, right? It's interesting that the models say that even this massive amount of sulfur aerosol injection in the stratosphere, there's no projection that it would make ocean acidification worse by dissolving in the oceans. Like
that's somewhat reassuring.
That's a little bit counterintuitive to me. I think that's a good question. Why doesn't enough of this stuff settle out into the ocean, which is after all 70% of the surface, to make the acidification worse?
Well, maybe that's a question we'll have to ask Dr. Keith. So maybe that's a good segue, because I know we're over time here, and I thank you everyone for hanging in there. But just a reminder, we will be going deeper into this topic of solar radiation management and with the aerosol injection, et cetera, with Dr. David Heath from Harvard on March 28th. And then we'll also be talking about less discussed potential mechanism in terms of solar reflectors changing the albedo of the Earth here on the surface with Dr. Yi Tao from MIR. That's on Friday. And I think that's going to be very interesting because there's a lot of practical potential advantages to that in terms of local effects that he will be able to talk to us about. So with those two topics, we'll be able to dive deeper into this, but I really appreciate, John, your time and your expertise here. I think that was so helpful in just understanding the basics and giving us all kind of more context for this, because as you said, this topic is not going away. We're going to be hearing more about this all the time. It's important that we're educated. So I really appreciate your expertise on this.
My pleasure. It was
huge appreciation as well. Thanks so much, John. Thanks for joining us. I just put a link in the chat for those upcoming webinars. And yeah, we hope to see you at those and at future ones. And Brian, leave us with our final.
Well, yes, to all of you, thank you for hanging in there with us today. This was really good. I know it was a lot of information, but it was really fantastic. Appreciate your attention and good luck with all your electrification projects. And if you have any questions on anything to do with electrification, give us a shout. If we can't answer it, we will find someone who can. Thank you all, and hope to see you at one of our upcoming episodes.